Find the area of an oblique triangle using the sine function and solve applied problems using the law of sines. Let's start by defining the law of sines. Given a non-right triangle, here's angle labeled alpha, beta, and gamma associated with A, B, and C as we're used to labeling, where A is opposite little a, so alpha is opposite A, B is opposite little b, so beta is opposite B, C is opposite little c, so gamma is opposite side C. So given a triangle like the one pictured, we have the sine of alpha over A equals the sine of beta over B equals the sine of gamma over little c. These ratios can be used to solve the following types of oblique triangles. Let's look at the different cases. Case 1 is AAS or ASA. When using case 1, you will need two angles and one side. The shorthand for this, as already said, is AAS or ASA. AAS stands for angle, angle, side, while ASA stands for angle, side, angle. Case 2, SSA, is also known as the ambiguous case. When using case 2, you need two sides and one angle. The angle cannot be between the two sides. That is SAS, and that is a different case. So this is key. Angle must not be between the two sides. That is a different case. SSA stands for side-side angle. Let's look at the first example. Applying the law of sines, angle, angle, side, solve the triangle given alpha equals 28.8 degrees, gamma equals 102.6 degrees, and C equals 25.3 centimeters. Let's begin with a sketch. I'm going to draw an obtuse triangle since the angle we're given is greater than 90 degrees. So there is my sketch of my triangle with my given angle gamma. I know that gamma is across from the side C, so this has to be side C. We're also given the length of side C as 25.3 centimeters. And the last thing we're given is angle alpha. The last piece of information we're given is angle alpha. So I'm going to let alpha be down here. So alpha is 28.8 degrees. So this must be side A. This must be angle beta, and this is side B. What do we not know? We do not know the length of side B. We do not know the length of side A. And we do not know the measure of angle beta. So those are the three pieces of information we're trying to find. Beta is the easiest piece of information. Recall, the angles of a triangle sum to 180 degrees. Or pi radians. This tells me that 180 degrees equals alpha plus beta plus gamma. So let us solve for the unknown angle, which is beta. This means that beta equals 180 degrees minus alpha minus gamma. And we know what alpha and gamma are. Alpha is 28.8 degrees. and gamma is 102.6. Using your calculator, you should end up with 48.6 degrees. So beta equals 48.6 degrees. Let's solve for side A and side B now using the law of sines. We know that sine of alpha over A equals sine of beta over B equals sine of gamma over C. And I can use any of these that I want to solve. If I want to find the length of side A, I can use either this or this expression. We want A to be the only unknown, so let's choose whichever one of these we know both the side and the angle for. For beta, I know the angle of 48.6 degrees, but I don't know the side length, so let's not use beta. But for gamma, I know both the angle of 102.6 and I know that the side length is 25.3 centimeters. So let's use gamma. So sine of alpha over A equals sine of gamma over C. So sine of 28.8 degrees over A equals sine of 102.6 degrees over 25.3. Using algebra, we can simplify this. Now that this is fully simplified, and that is I have isolated A, I just need my graphing calculator to find my solution. And bear with me, I'm going to move some things up a little bit, just so this doesn't look so crowded. So pull out your graphing calculator. Here's my graphing calculator. The first thing I need to do is check my mode. And sure enough, I'm in radian mode, so let's go ahead and switch that to degree mode. Now that I'm in degree mode, I can compute 25.3 times the sine of 28.8, and this entire quantity is divided by the sine of 102.6 degrees. That gives me A equals about 12.5 centimeters. Sine of beta over B equals sine of gamma over C. In case you're wondering why I use gamma over C rather than using sine of alpha over A, this information here we were given by the problem, so there's no doubting that it's correct. If for any reason you made a mistake here, you round it off, your answer could be off for this side B. So it's always best practice, when possible, to use the given information rather than what you've computed. So let's fill in all the known blanks. We have sine of 48.6 degrees over B equals sine of 102.6 degrees over 25.3. Let's simplify this again. Now that I have B isolated, I can use my graphing calculator to figure all of this out. So pull out your calculator. Here is my calculator. I'm going to go ahead and clear this screen. And now I'm going to compute 25.3 times sine of 48.6, this entire quantity, divided by sine of 102.6. And we end up with B is about 19.4 centimeters. So we have finished solving everything. We know that A equals 12.5 centimeters, B equals 19.4 centimeters, and beta equals 48.6 centimeters. Let's look at the next page. Example 2. Let's apply the law of sines. Using this triangle below, we're given two angles and a side between the angles. Beta, side C, and side A are unknown. Beta equals 180 degrees minus 98 degrees minus 43 degrees, which is just 39 degrees. Now let's solve for A. We know that sine of alpha over A equals sine of beta over B. So sine of 98 degrees over A equals sine of 39 degrees over 22. So A equals 22 times sine of 98 degrees divided by sine of 39 degrees. And I skipped the algebra here. So using my calculator, I end up with A equals about 35. And I'm rounding to the nearest whole number. Let's find side C. I know that sine of gamma over C equals sine of beta over B. So sine of 43 degrees over C equals sine of 39 degrees over 22. So C equals 22 sine 43 degrees divided by sine 39 degrees. So rounded to the nearest whole number, I end up with C equals 24. Next, let's discuss SSA, that is the ambiguous case and possible outcomes. Oblique triangles in this category may have the following outcomes: no triangle, one triangle, or two triangles. Given known sides A and B and angle alpha, given known sides A and B and angle alpha, we may have no triangle, one triangle, or two triangles. A quick note: all the cases given below assume alpha is an acute angle. The cases for alpha being an obtuse angle are a little bit different. We are just focusing on the acute cases. Now, we also see an H here. And what is H? So for that, I'm going to draw a quick sketch. Say we have this triangle here. And let's label our triangle. Let's say we're given alpha, so this is side A, and we are given B, and that's all we're given. We're given two sides and an angle not between the two sides. Well, the height of this triangle is right here, and this forms a right angle. So we can find H as follows. We know that sine of alpha equals opposite, which is H, over the hypotenuse, which is B, and that is of this triangle here. So this right triangle is formed, and we're using that to find H. So H equals B times sine of alpha. So for all of these cases, we might be given sides that are labeled a little bit differently. In order to find H, use the side not associated with the angle you're given. So if you're given A, gamma, and C, then you would use A sine gamma. But when in doubt, you can always draw a sketch and figure it out. So now, if A happens to be less than H, and of course now we know that H equals B times sine of alpha, Then we have a no triangle. That would look something like this. We'd have a really long side B. We'd have our angle alpha. And then if we try to drop A somewhere, here's the height of this triangle that may be formed. But A is too small. Here's A. It could be here. It could be here. No matter where we place A, it's not quite going to reach the bottom. If we try to adjust this by, say, making this line in this direction, we'd be changing the alpha and would no longer have the information given. Let's look at case 2. If we've computed H using the side not associated with the given angle and the one and only given angle, and found out that A equals H, then we have a right triangle. Here's alpha. Here's A, which is equal to the height. And here's B. So in this case, we have a right triangle. We can also still have an oblique triangle, and that would look something like this. So in this case, alpha may be here. This here is my height. So this is side A, and this is side B, and this is an oblique triangle. And so these are our two possible outcomes when we're given an A that is equal to H or an A that is greater than the side B. Finally, we have the two triangle case. So here we figured out what H is. We figured out that A is larger than H. And of course, when I say H, I mean the angle associated with the side. So since A and alpha are opposite each other, that means alpha and A are associated, so A is the side that I'm really interested in. I know that A is not equal to H. I know that it's not smaller than H, so I'm going to automatically go straight to this case, and that looks something like this. So this is our first triangle that's formed. Here's alpha, here's A, and here's B. Of course, this is my height. But I can also place side A off to the left. So this would also be A. And in this case, this second triangle that's formed is an isosceles triangle. Since this is an isosceles triangle, I know that this angle and this angle are going to be equal, as well as this side and this side, which we can already see because they're both of length A. But in case you don't see that, I'm going to briefly go over how we can figure out that these two angles are equal in the next example. So let's go ahead and move on to example 3.